Welcome back. Problem 12-16. This problem is taken from chapter number 12, that is deflection of beam and shaft, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the pipe can be assumed roller supported at its end and by rigid saddle C at its center. The saddle rests on a cable that is connected to supports. Determine the force that should be developed in the cable if the saddle keeps the pipe from sagging or deflecting at its center. The pipe and fluid within it have a combined weight of 125 pounds per feet. EI is constant. So you can see this is the pipe. The, the ends are assumed to be roller supported, and at point C there is a saddle which keep it from deflecting at this point. And due to the weight of the pipe and the fluid it carries, there is a uniformly distributed load which having magnitude of 125 pounds per feet. So due to this loading, the beam will behave like this. Clear? So we have to find that the force that is developed in this row. So let's start with the solution. So first step is that we will draw the free body diagram of this pipe. First I will draw the free body diagram. So this is the pipe. Clear? If you remove the end support, so there will be a reaction force, and since the beam is symmetrical, loading is symmetrical, so the reaction force will be same on the both end. Let this reaction force is P, that will be upward. And at the center C we have a saddle which exert vertical reaction force on this pipe, and this force is also taken as upward. So I will take it upward at the mid. This force is, let this force is F, that these saddles apply on this pipe, and there is a uniformly distributed load. Clear? Due to the weight of the pipe and the fluid that it carries. And we will take this uniformly distributed load that is given as 125 pounds per feet. Okay, the distance between these two are 12.5 feet, and this distance is also 12.5 feet. Now we will find the reaction forces P by using equation of equilibrium, and equation of equilibrium that we'll use is that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So you can see one force is P, the other force is F, the third force is P, and there is uniformly distributed load. So this uniformly distributed load when converted into point load, so it will be equal to this load 125 pounds per feet into the length over which it acts. So total length is 12.5 plus 12.5 is 25, and that will be acting downward. So I will write P, that is upward. Clear? Plus P, there is another P which is upward, plus F minus 125 into length 25 is equal to 0. So we will write 2P plus F is equal to 3125. Let this is your equation number A. Now the second step is that we are going to find out the reactions force. So we will use equation of elastic curve in order to find this load. So how we will find this? So we know that EI into d square V over dx square is equal to moment. So what we will do is that we will cut this beam at any section between A and C, and if I draw the free body diagram, so it will be like this. This is point load P, our reaction. Let this distance where we cut this beam is X, Clear? This is the x distance. This is the x distance. And there is a uniformly distributed load that is acting downward. And this load is 125 pounds per feet. 125 pounds per feet. And when you cut it at this section, so there will be a shear force that will be acting downward, which is V, and there will be external moment M. So we'll find this moment by using equation of equilibrium, that sum of all moments about point 1, and this is point 1, is equal to 0, taking the counterclockwise movement as positive. So about point 1, one moment is due to this load P into perpendicular distance is x, and this is producing clockwise movement, so it will be negative. Clear? So I will write minus P into x. The second moment that is produced due to this distributed load 125, and when it is converted into point load, so this will be acting, this will be 125 and the length is x, and that will act at a half of this total length, which is equal to x by 2. So, and this is also producing this load into perpendicular distance is x by 2, and it is producing counterclockwise movement, so it will be positive. So I will write plus 125 into x by 2, and the last moment is this reaction moment, which is counterclockwise, so it will be positive. So I will write plus m is equal to 0. So from here you will get this moment will be equal to P into x minus 125 x square over 2. So this is the moment equation. Let this is equation number 1 and this is equation number B. So put equation 1 in equation B. So what you will get is that EI into d square V over dx square is equal to px minus 125 x square over 2. So integrate this equation, integrate it, you will get EI into dv over dx is equal to px square over 2 minus 125 x cube over 6 plus there is a constant of integration which is c1, and you can, if you simplify it, it will be equal to px square over 2, and this minus 125 divided by 6 will be minus 20.833 x cube plus c1. Okay, let this is your equation number C. Now what we will do is that integrate this equation, integrate equation C. So what we will get is that EI into V, which is deflection, is equal to px cube over 6 minus 20.833 x power 4 divided by 4 plus c1x plus c2, and that will be equal to px cube over 6 minus 5.208 x power 4 plus c1x plus c2. This will be equal to EI into V. And this is your equation number D. Now C1 and C2 are unknown constant of integration, so we will use boundary conditions in order to find them. So boundary conditions. So first boundary condition is that at x is equal to 0 we have deflection is equal to 0. Let me show you over here. Here x is equal to 0, we have deflection is equal to 0 because there is a roller support. Clear? So what we will do is we are going to put it in equation number D, because equation D is about deflection. Okay, So when you put x is equal to 0, v is equal to 0, so ei into 0 is equal to p into 0 cube divided by 6 minus 5.208 into 0 power 4 plus c1 into 0 plus c2. So we will get c2 is equal to 0. Now we will use another boundary condition, that is at x is equal to 12.5 feet, we have deflection is equal to 0. Because it is given that at point C there is a saddle, so at x is equal to 12.5 feet, uh, this saddle help us in this saddle help us from sagging the pipe or deflecting at its center. So it means that deflection will be equal to 0 at this point. So put it in equation number D. Put in equation D. So when you put it, EI into 0 is equal to P into 12.5 cube divided by 6 minus 5.208 into 12.5 power 4 plus 12.5 into C1, and C2 is equal to 0. So if you divide 12.5 on both sides, so you will get 0 is equal to P into 12.5 square divided by 6 minus 5.208 into 12.5 power 3 plus C1. Okay, let this is your equation number 2. Or you can also, okay, let me simplify it. So what we will do is that C1 will be equal to, from here you will get C1 will be equal to 5.208 into 12.5 cube minus P into 12.5 square divided by 6. Okay, so this is your equation number 2. We will use third boundary condition, and that third boundary condition is that at x is equal to 12.5 feet, we have deflection or slope dv over dx will be equal to 0. So let me show you here. This beam will deflect like this. So you can see that here this deflection is equal to 0. So if you draw tangent to this curve, so that will define slope, and this slope will be equal to 0. So put it in equation number C. Put in equation C, and equation C is this one. So when you put it, EI into dv over dx is equal to 0, and P into x is 12.5 feet, so P into x square over 2 minus 20.833 into 12.5 cube plus C1. So here we will get 0 is equal to P into 12.5 square divided by 2 minus 20.833 into 12.5 cube plus C1. Okay, so put this is the value of C1. Put this C1 in this equation. So when you put it, put C1 in equation number, let this is equation number 3. So you will get 0 is equal to P into 12.5 square divided by 2 minus 20.833 833 into 12.5 cube plus C1, which is equal to 5.208 into 12.5 cube minus P into 12.5 square divided by 6. So when you solve this, you will get the value of P, and this P will be equal to 585.94, and the unit will be pounds. Now you have this P clear, so you can just put it in this equation number A. So you will get this F will be equal to 3125 minus 2P, which is equal to 3125 minus 2 times minus 2 times 585 580 585.94. So you will get this F will be equal to 1953.12 pounds. So this is the reaction force that this saddle applied on this pipe. Now what we will do is that you can see from this figure, this saddle applies force upward. So as per Newton's third law, this force acts downward on this cable, causing the tension in this cable. So we will take point C, free body diagram at C. So this is your point C, clear. So where you have this reaction force that is downward, and this is 1953.12 pounds, and due to this there will be a reaction or tension in these two cables. And let these two forces are represented by R. These are making an angle theta with this horizontal. So we are interested to find this R. So what we will do is that you can see this distance is given as 12.5 feet each. Similarly, this distance is also 12.5 feet. Okay. And this distance, that is this vertical distance, this is 1 feet. Let me show you over here. You can see this vertical distance is 1 feet and this horizontal distance is 12.5 feet. So what we will do is that by using Pythagoras theorem, this will be equal to 12.54 feet. This length will be AC will be equal to 12.54 feet. Okay, so we are interested to find out this R. So what we will do is that we will apply equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. This force is downward, so I will write it minus 1953.12, and there are two components of this. One is this one and other is this one. So we will take the vertical components only. So this vertical component will be equal to R sine of theta. So I will write 2 times because one force is there and one other force vertical component is there. So 2R into sine of theta is equal to 0. So I will write minus 1953.12 plus 2R, and if you take sine theta, so sine theta is equal to perpendicular over hypotenuse. So perpendicular is 1 and hypotenuse is 12.54. So I will put the value over here, 1 over 12.54. Okay, that is equal to 0. So from here, when you solve this, so you will get this force in the cable comes out to be 12246 pounds. or you can see 12.246 kips, which is the answer of this question. So 12.246 is the answer of this, and this is the force that develop in the cable, which causes no sagging in this pipe. And that was all about this problem 12-16. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.